So there I was browsing the math subreddits because I like to answer questions there when I can. Came across this one. I'm not sure if you can see it because it might be kind of tiny in my recording box, but it's about finding the area in a region trapped between a few functions. This is going to be a good old application of integration problem. And I thought about drawing a picture, exporting the picture, typing in a bunch of text into a reply box, and figured, if I'm going to be solving the problem, why don't I just record myself instead of cut out all that middle stuff? So here we are. The three functions at hand are 2y equals 3 square root of x, y equals 4, horizontal line, and 2y plus 3x equals 6, sloped line. We're going to draw the region inside those three functions and then figure out how to solve for the area. So the drawing of the region and using that to delineate limits of integration, that's the bulk of the battle here. Once you've set up the integrals, I'm assuming that the integration can proceed relatively easily. So I'm going to focus on drawing this region and setting up the integrals that are needed to calculate the area in this pocket that gets formed. So the three functions again, 2y equals 3 root x, y equals 4, and 2y plus 3x equals 6. So let's get some basic information first. Y equals 4 is horizontal line. For this line here, let's draw it by coming up with the intercepts. For example, when x is 0, y is going to be 3, right? Because if x is 0, we get 2y equals 6, y is 3. If y is 0, then we get 3x equals 6, so x is 2. All right. This function here is also known as y equals 3 halves square root of x. So it's certainly going to begin at the origin. It's going to have the shape of the square root curve. It's just going to be a little bit bended differently than straight up y equals root x. And again, y equals 4, horizontal line. So I'm going to try to draw this picture. Sorry for my jagged freehand on a tablet type of thing axes here, but let's put let's do that. So I'm going to put the intercepts of the sloped line 0, 3 and 2, 0. So that is going to go this way, and y equals 4. Well, let's put that there. I'll draw that like a dashed line, for example. And then y equals 3 halves square root of x. Well, that's going to start here at the origin. I'll make this a different color just to keep it going. It starts at 0, 0. When x is 1, y is going to be 3 halves, so it's going to go through that point roughly, and it's going to have that general square root type of bend to it. Okay, so this is the set of lines that we're talking about. Now notice that this curve is going to keep going, of course, out of the field of view. Every time I record, the dog knows, because we get the school buses driving by, we get the post office dropping off the mail, so I'm going to pause and see if he shuts up. All right, the little bastard stopped for now. So the region that we're trying to find the area of is this one here that I'm shading in. And so what we need to find is perhaps this point of intersection right there. Not perhaps, that will be useful information. And then again, off the screen here, but somewhere, farther out there, that's the wrong place for it, is going to be a point on the line y equals 4 where that square root function cuts that. And so then we've got this pocket, horizontal top, straight slanted side, and sort of a bendy side. We've got that pocket. That's the area that we're looking for. Okay, so what are the limits of integration that we want to use for this problem? Well, it depends whether we're going to integrate with respect to x or with respect to y. Okay, so let's compare and contrast those two options. We are the calculus ant. Little antennas and little ant legs, okay? And we are going to be walking down the x-axis and looking up into the region that we see, right? So there, and there, and there, and there, and there. And the thing that we're trying to figure out is how many sets of lower and upper bounds do we need to capture this region? And it looks like we would need two regions separated because... Make sure I'm not overloading with red. Dang it. There we go. Go away. Right here, at this point of intersection between the straight line and the square root curve, the lower bound of our region is the sloped line, and the upper bound is the horizontal line. To the right of this little cut, the lower bound of the region is the square root curve, and the upper bound is the horizontal y equals 4. So if we want that total area, and we're going to integrate with respect to x, meaning we are the calculus ant, we're walking along the x-axis, and we're going to start at a point and end at a point, and we're looking up towards our region, and we're going to do an integral of upper function minus lower function. On the left half of this picture, we have a different lower function than on the right half of the picture, which means we need to set up two different integrals. Okay? How about if we integrate with respect to the y-axis? Now, I understand that this picture is getting quite busy, but if we are the calculus ant and we are now walking, there's his little antennas and his little ant legs again, we are walking this way. We're walking up the y-axis, and now this time we're kind of looking outwards. And we want to decide, what do we see as the upper, quote-unquote, or farther away boundary and the closer boundary from us? And that will determine the upper and the lower curve relative to the y-axis that we might integrate, the upper minus the lower. Again, along the x-axis, we have to break this into two integrals because in one region we have a different lower bound than in the other region. But if you look at this is really getting messy, and I'm about to redraw it. But no matter where we are in our region as we walk up and down the y-axis, in one direction, the right-hand boundary, or the upper boundary, is going to be the square root curve, and in the other direction, the lower boundary is going to be the straight line. So it seems to be a little bit more advantageous to integrate with respect to y. Now, you can't go wrong by integrating with respect to x. You'll just have to set up and evaluate two integrals, whereas with respect to y, we can do it with one. Okay, so I'm going to clean the page up here. Okay, so this is still kind of sloppy, but it's cleaner than the mess that I made of the previous picture. So what we're going to do is we're going to find the area of this region by integrating with respect to y. And again, remember that means we're going to cover this entire interval, or this entire region, by walking up and down the y-axis and integrating the upper function minus the lower function. So we need to know this lower limit right there. That's the only intersection that we need, okay? Because if we're walking up and down the y-axis, our upper, or farthest in the positive direction, our upper curve is the root curve, and the lower curve is the sloped line. So we need to find out where the curve, I'll write it as 2y equals... No, I'm not. We need to know where y equals 3/2 square root of x intersects with 2y. What was that curve? 2y plus 3x equals 6. Doing this on the fly is so much fun, right? We're looking for that intersection. Well, see, I should have kept it as 2y because that root curve originally was presented as 2y equals 3 square root of x. So when we ask this curve where it intersects this curve, the intersection happens when 2y plus 3x is 6, or when 3 square root of x plus 3x equals 6. So we need to solve this for x and then return a y coordinate. Now, there's some algebra that you can do here, but I will suggest that if we just look at that and think really hard, we can figure it out. How about when x is 1? When x is 1, we get 3 times 1 plus 3 times 1 equals 6. So x is 1 satisfies that point of intersection. And when x is 1, what's the y coordinate that goes with that? Do we check the sloped line or do we check the root curve? It doesn't matter. They're intersecting. We can check either one because it's going to be the same point. So I will use this one. And when x is 1, y is 3/2. So this is no longer a question mark. This is now 3/2. Okay? And so now we are going to integrate, or I'll squeeze this in on the side, but I'm going to go to a fresh page. From 3/2 to 4, we're going to put some stuff in there and integrate with respect to y. And then the info that goes in here is the upper function minus the lower function, but we have to have these written with respect to y. So that's going to be the last deal here. So I'm going to flip over. I'm going to draw this really quickly one last time. With less detail, here is our region. Uh-oh, here comes the mail truck on our side of the street. The dogs are going to start barking again. Remember that this is 3/2. For y, this is 4. So we're going to integrate from 3/2 to 4 with respect to y. The upper curve is the square root function minus the lower curve, which is the straight line. And so all we need to do with those is visit their given equations and make sure that we've written the functions as a function of y. So one of them was, what, 2y equals 3 square root of x. That's the one that's going to go here. Well, in terms of y, that is 2y over 3 equals square root of x, or 2y over 3 squared equals x. And so (2y over 3 squared). Whoops, I put it in the wrong spot. This is supposed to be the upper curve. Dang it. 2y over 3 squared. Okay. And then for the sloped line, the original function there was, I gotta go recapture it, 2y plus 3x equals 6. Or in other words, x or 3x equals 6 minus 2y, or x equals 2 minus 2/3 y. And again, sloppy, but there it is. So that is the integral that needs to get solved. I'll write it down once more to clean it up. Integral from 3/2 to 4, 2y over 3 squared, minus, come on, the integral of 2 minus 2y over 3, dy. Okay, so again, I'm going to leave it at that. That is hopefully where anybody, the poster or anybody else, could take this and run with it to get the final value. But again, the overall story was You got a horizontal line, you got a slope line, you got a curvy square root thing. Find the area in the pocket formed by those three. We notice that if we're marching along the x-axis and looking upwards into our region, depending on where we are, we see a different lower function. And so that means to calculate the total area, we would have to split the calculation into two integrals, one with capturing one lower boundary and the other one capturing the second lower boundary. Whereas if we're marching up and down along the y-axis and we're looking out to see the boundaries of the region, we always see the square root function as the upper region with respect to y. We always see the slope line as the lower boundary with respect to y. So integrating with respect to y, we can get that done with one integral. And that integral is, hopefully, this one.